Standard two-dimensional shapes, like squares, are flat, but the objects we interact with every day occupy physical space. To represent this space, we add a third dimension to length and width, height, or depth. Look at this Rubik's Cube. This depth allows it to be held, stacked, and viewed from multiple angles. We describe these objects using three specific terms. First are the faces, the flat surfaces of the shape. Edges are the line segments where two faces meet, and vertices are the corner points where edges intersect. Faces, edges, and vertices form the structural framework for every straight-sided 3D shape, or polyhedron. Mapping them allows us to measure and define the space the object occupies. For these shapes, there is a fixed relationship between their components, known as Euler's formula. It states that faces plus vertices minus edges will always equal 2. For a triangular prism with 5 faces and 9 edges, let's calculate its vertices. Identify knowns. F equals 5, E equals 9. Substitute into Euler's formula. 5 plus V minus 9 equals 2. Simplify, and we solve for exactly 6 vertices. Keep in mind that this formula only applies to polyhedra. It will not work for shapes with curved surfaces, such as cylinders or spheres. Euler's formula provides a reliable method for verifying your observations, ensuring that your breakdown of a polyhedron's components remains mathematically consistent. Representing these solids on paper creates a challenge, as a two-dimensional surface lacks natural depth. We use specific drafting techniques to simulate the third dimension. In an oblique sketch, you draw the front face to its true size, then draw depth lines receding at an angle of 45 degrees. While easy to draw, these angled lines often distort the true proportions of the object. Isometric sketching offers more realism. By using a special dot grid, we can draw the 3 main axes, length, width, and height, at equal angles, maintaining a consistent scale for all dimensions. Following these grid rules creates a proportional representation that is useful for technical blueprints and architectural drawings. To draw a cuboid with a length of 5, a width of 3, and a height of 4, start with a blank isometric grid. Select a starting point on the grid to represent the bottom front corner. Draw a vertical line upward exactly 4 units to establish the height. From the starting point, draw a line 5 units to the right along the 30-degree axis to set the length. Then, draw a line 3 units to the left to establish the width. Complete the cuboid by drawing the remaining edges parallel to these 3 axes. Remember that in an isometric sketch, any lines that are parallel on the actual object must remain perfectly parallel on the grid. By counting the spaces between dots, you can turn a flat surface into a measurable representation of a 3D object. Beyond drawing, we often need to determine the total volume of complex or combined 3D shapes. Counting individual unit cubes can be difficult because the structure of the shape often hides internal cubes from view. To count accurately, we visualize the object as a series of separate horizontal layers. Volume estimation reduces a complex structure to a vertical stack of individual addition problems. Take this stepped pyramid. To find its total volume, we will count the cubes in each tier starting from the top. The top layer is simple. It is just 1 unit cube. The middle tier is a square measuring 2 units by 2 units. This gives us a total of 4 cubes for the second layer. The base layer is a larger square, 3 units by 3 units, containing 9 cubes. Note that these 9 cubes include the hidden ones in the center that support the layers above. Adding these layers, 1, 4, and 9, results in a total volume of 14 unit cubes. Developing these skills, from counting vertices to calculating volumes, provides the specific tools needed to describe 3-dimensional objects. Good luck on your exams.